right, welcome to the afternoon session. Our first speaker is Martijn Kool from the University of Utrecht, and he's speaking about gauge origami and autonomous virtual cycle.
Thank you for the introduction. So thanks to the organizers, it's great to be here. It's a very inspiring workshop. So yes, I'll be talking about a joint work in progress with Noah Arbesfeld and Woonam Lim. And so on gauge origami and autonomous virtual cycles. And along the way, I'll also talk a bit about another work in progress with Rennemo, which will play a key role here too. So this talk is about understanding a certain quiver that Nekrasov writes down in the physics literature. But before going to his quiver, let me put on some motivation by talking about the traditional ADHM quiver. So the traditional ADHM quiver plays an important role in gauge theory and enumerative geometry. So what is it? So we'll be fixing, a n-dimensional complex vector space V and an r-dimensional complex vector space W. And we'll look at the following quiver drawn here. So we have a vertex with W, a vertex with V. We have one ingoing arrow I and one outgoing arrow J, and then these two loops x1 and x2. So representations of this quiver are just linear maps, x1, x2, I, j, between these vector spaces. And we impose some conditions. So the conditions are this equation here. So we want the commutator of x1 and x2 plus I composed with j equal to 0. So this is the ADHM equation. And then there's also a stability condition. So we require that if we act with polynomial expressions in the loops on the image of I, that we generate all of V. That's this condition here. So then you can act on this by change of coordinates of V. And because we have this stability condition here, this will be a free action. So we can form this quotient, and this will be our moduli space MRN of representations of this quiver. So sometimes I'll drop the R and the N and simply write M. And one special case you can look at here is by taking this rank here of W equal to 1. Then it turns out that you can actually show from these equations that J has to be 0, and you found a quiver description of the Hilbert scheme of n points on C2. So there's a lot to say about this quiver and this moduli space, but I'll only highlight three properties. So this M is smooth of dimension 2Rn, and one key property is that the tangent bundle and cotangent bundle are isomorphic. So in this sense it's symplectic. That's the first property. So for the second property, we're interested in calculating invariance, integrating classes over this moduli space. But one problem we're faced with is that this moduli space is non-compact. But fortunately, there's a big algebraic torus acting on this moduli space. So we have a C star squared, which is just scaling the loops. And we have a C star R, which is the diagonal action on W. So here we had these two loops, x1 and x2, and in this space W. And then the fixed locus is actually very easy. It's 0-dimensional and reduced. So what do we want to do? Well, let's just look at the simplest insertion. We integrate 1 over this moduli space, MRN, and we interpret this as an equivariant integration. So by the Atiyah-Bott localization formula, what this means is we're summing over all the fixed points, P, and for each fixed point we calculate 1 divided by the Euler class of the tangent representation of the moduli space at the point P. And then we put them all in the generating function, so the rank here is fixed, and we sum over all n. So this is the simplest case of what is known as a Nekrasov partition function. And in a way, this is a building block for many more complicated invariants. So on Monday, we saw Fafa-Witten invariants in Richard's talk. So these can be used to calculate Fafa-Witten invariants. And they can also be used to calculate Donaldson-Thomas invariants. So it's sort of an important building block. And a third property that's important today is a sheaf description of this moduli space, which is due to Bart. So instead of looking at representations of this quiver, you could look at pairs E, phi, where E is a rank R torsion-free sheaf on the projective plane. And what is phi? So we fix a line L infinity in the projective plane, and phi is just an isomorphism of the restriction of E to the line with O of R. And then finally we fix the second Chern class of E to be n. This number is sometimes called the instanton number. So this is the sheaf description of the quiver moduli space. So now let us get to the quiver we're actually interested in today, which was introduced by Nekrasov. So first a little bit of notation. So by 6 bar, I mean the subset of all numbers a, b, where a and b range between 1 and 4. And 4 bar is the set consisting of 1, 2, 3, 4. And then what do? There's some further notation. For any a in 6 bar, we denote by a upper bar the complement of a. And now we also fix some vector spaces. So as before, V will be an n-dimensional complex vector space, but now we have a whole bunch of framing vector spaces. So for each A in this set 6 bar, we have a moduli space C of Ra. So what is the quiver now? So the quiver, it has one internal vertex V, and then it has 6 external framing vertices W12, W13, all the way up to W34. And then for each of them we have an ingoing arrow IA and an outgoing arrow JA, and 4 loops x1 up to x4. Okay, so we call this the origami quiver. We look at representations, so linear maps between these vector spaces. And then Nekrasov tells us to look at the following set of equations. So for each capital A, consisting of A smaller than B, we have a sort of ADHM equation. So simply commutator XAXB plus IAJA is 0. And then he tells us whenever we go in with an arrow IA and we go out with the complementary arrow JA bar, we also should get 0. And then we have this final set. If we take little a bar in capital A bar, so the complement of A, we have that if we first go in with IA and then act with XA bar, we get 0, and the same for the J. And then finally there's a stability condition, it's the same as before. If we act with polynomial expressions on the joint images of all the IAs, we generate all of V. And then also as before, there's an action of this general linear group, so coordinate transformations on V, and because of stability it will act freely. So we can take the quotient and we have this moduli space. So this is the moduli space we'll study. And there's a related, somewhat easier, well at least in terms of the quiver, easier moduli space, sort of a cousin of the previous one. So we also look at this moduli space where, which is just the Hilbert scheme of n points on C4. So we have one vertex with vector space C, one vertex with V, which is this Cn, and then 4 loops. And this time the relations are simply that all these loops need to commute. So this is a matrix description of structure sheaves of 0-dimensional subschemes of C4. And as before, we have this stability condition again, and act here with the general linear group. Now, the goal of today's talk is to find analogs of these properties 1, 2, 3, and 4 on the second slide. So these properties here. But we're immediately faced with a big issue. These spaces are very singular. So as an example, let us take R12 and R34 equal to 1, and all the other RAs equal to 0. And let's look at instanton number 1. So in this case, the equations are sufficiently easy to really see what the moduli space is. It's simply 2 affine planes where joined by a P1 which connects their origins. And so this is singular. And then we also know, of course, that for Hilbert schemes of points on C4, if you have 4 or more points, you're also singular. So we have to be happy
we have to deal with very singular spaces. Yeah.
If you go back to the previous
Yes.
slide, is this a closed set inside of an ADHM representation where I just direct sum the W's? If I direct sum the W's, I'm getting...
Yeah, so actually that will sit as a sort of, they will sort of map to this space, which will come at the very end of the talk. So they will sit as a fixed locus in here.
So they're closed in there and they're fixed inside of their bus.
And yeah, so yeah, I'll show a precise relation later. Yeah.
Could you say example one again? Was that a picture of the moduli space?
This is the actual moduli space. Yes. Yeah. Right. So in this case, what do you have? You have so we have only a W12 and W34, which are both just one-dimensional. V, which is one-dimensional. So you just have a whole bunch of scalars that needs to satisfy these equations here, plus this stability condition. Then if you work it out, you'll find this space here. Okay, so we have these singular spaces, but they come with extra structures. So both of these spaces, MRN and Hilp NC4, come with extra structure, which I'll tell you about in this slide. So what I'll say henceforth about the Hilbert scheme is joint work in progress with Jürgen Rennemo. So both of our moduli spaces arise in the following way. So let's, in general, consider the following setup. We have some smooth connected variety A, with on it an even dimensional quadratic vector bundle, E. So quadratic vector bundle means we have a fiber-wise non-degenerate symmetric bilinear form, little q, and we have a section of this quadratic bundle, and we require that this section is isotropic, so the quadratic form vanishes on it. And let M be the zero locus of this isotropic section. So then if you read O. Thomas, they will tell you to write down the following diagram. So let us denote by I the ideal sheaf of M inside of A. So they tell you that you should look at the following diagram. So if you take the differential of the section S here, you map from the tangent space of the ambient space to E. And then you can use the quadratic form to go to E dual, and then just put the dual of this section here. And since S is isotropic, this is actually a complex. The composition will be zero. So here on the top you see a three-term complex of vector bundles. And like in Monday's talk, we'll denote this, we call this the virtual cotangent bundle, omega m ver, and its dual will denote by T m ver. And then what we can do is we can map to the cotangent complex of M, or rather its truncation, simply by taking the dual section. So this will surject onto I modulo I squared, and then you can take the Kähler differential to get to omega of A. Complete the diagram. So this then produces for you, in the terminology of Berend van Tekkie, a three-term obstruction theory. But it has some additional good property. It's symmetric. So you see that this top complex here is self-dual up to a shift. So in some sense it's also symplectic up to this shift. So this is a three-term symmetric obstruction theory.
So I guess the Nekrasov quiver can be upgraded to a DG quiver, can it?
Probably, yeah, but we don't need that. So I'm actually, when I say this for this talk, I won't be meaning this as an actual shifted symplectic. We don't need that at this point. So having this model is enough for us. So how do we apply that in our setting? So this is a general setup. So how do we apply this in our setting? So what do you take as your smooth ambient space? You just take, again, the representations of the same quiver, but then without the relations. So that will give you the smooth ambient space. And the sections are also easy. You just take the equations that you want to satisfy. So those will be the section. And that also dictates to you which bundle you should take. But the interesting part that is very specific to these quivers that I wrote down, the origami quiver and the Hilbert scheme quiver on C4, what's very special is that they have this quadratic form for which the relations are isotropic. So I won't write this down in general for the origami quiver, that requires quite some notation, but for the Hilbert scheme it's relatively easy to write down. So for the Hilbert scheme, remember, representation without the relations is just a tuple of four matrices and a vector I.
So what are the relations? The relations were just the commutators between the matrices. So our section over this point is just all the commutators. And where does this live? This lives in 6 copies of the endomorphism algebra V. So the direct sum over A smaller than B of end V. Okay, so that's the easy part. And then the interesting part is that there's this quadratic form on the fiber. So if we use fiber coordinates VAB, you can look at the following form: trace of V12, V34 minus V13, V24 plus V14, V23. So the point is, if you plug these commutators into this quadratic form, you get 0. So this is very special to this Hilbert scheme of points on C4 case. And the claim is you can write down something similar, but more complicated, in the origami setting. So in some sense, this should be viewed as the analog of property 1. So these moduli spaces are very singular, but their virtual tangent bundle and virtual cotangent bundle are isomorphic. In that sense, they are also symplectic. So this is property 1. Are there any questions? So now that we have this, the first problem you're faced with is we don't have a 2-term obstruction theory, so we do not have a Behrend-van Tecke-Li-Tian virtual cycle. However, Borisov-Joyce and O. Thomas, they do construct a virtual cycle in the setting we're in. In fact, their construction is much more general. It doesn't need your moduli space to be globally the 0 locus of an isotropic section, but in particular it will apply to our setting too. So for their construction, you need some extra data, which I'll talk about now. So you need what's called an orientation. So what this is in our setting is you need isomorphism between the determinant of our quadratic bundle and O, and it needs to have the property that its square is the determinant of the quadratic form. So how do you produce orientations? So one way of producing orientations very concretely is as follows. You pick maximal isotropic subbundle lambda. So then in the short exact sequence, the co-kernel can be identified with the dual of lambda. So this short exact sequence for you produces an isomorphism of the determinant of E with O. So any lambda will give you orientation O of lambda. So when you fix this data, they will produce for you a virtual fundamental class in the Chow group with rational coefficients. And the degree it lives in is half the rank of your virtual tangent bundle. And I won't tell you in general what their construction is, but I will actually go into some detail what it is after localization. So I'll focus on what this class looks like after localization. But one good property to mention already at this stage is if your orientation is O of lambda and you push this virtual class forward to the ambient space, then it's something very nice, namely just the Euler class of this maximal isotropic subbundle. So it's sort of half of your quadratic bundle. So the point that we're now faced with, however, is that our moduli spaces are not compact. So we want to do some form of localization. So first, let us go back to the general setup, so that by which I mean the general setup we have on this slide, and let's put some more data on it. So we're in this slide. Now we're going to put torus actions here.
Martijn,
Yeah.
are all your virtual dimensions even?
Yes, so in this case, I assumed here that we're dealing with, oops, keep mispressing. So yeah, here I assume that E is even. So let us assume that we have an algebraic torus acting on our space A, and that the vector bundle is T equivariant and the section as well. And let us assume that the quadratic form is T invariant. So then this diagram that I wrote down with the 3-term obstruction theory is entirely equivariant. And let us also make an assumption, namely the fixed locus is 0-dimensional and reduced. So then you may guess at least the general shape of the localization formula. So what O. Thomas tell you is that after localizing, you're summing over all the fixed points, and what do? So now, since this T ver at a fixed point is self-dual, we know that its Euler class is a square. So you know that you can take a square root of this Euler class here. But the complicated part of this formula is that which square root should you take? So the type of square root you should take here is dictated by which global orientation you pick, as I'll explain on the next slide. So I'll make this explicit in the case that we actually have a splitting of our quadratic bundle into E plus its dual. So lambda here is a T equivariant maximal isotropic subbundle. So when you have this splitting, at least you can write down a square root. You can simply take the Euler class of the tangent bundle at the fixed point minus the maximal isotropic at the fixed point. But then, of course, you still haven't nailed down this sign. And in this subject, often we dislike signs and we work modulo signs. But in this subject, everything is about the sign. So here, it's really about what is this sign. So how should you take the sign? So the key observation is that if we go above a fixed point P and we look at our quadratic bundle and we take the fixed part, so it's some T representation, and we take the fixed part, then we actually have two maximal isotropic subspaces of this space. So on the one hand, we have our lambda. We simply restrict it and take the fixed part. So this lambda is the one that we use to pick our orientation. But then there is a second one. So since we assume our fixed locus is zero-dimensional and reduced, you can actually show that the differential going from the fixed part of the tangent space at the fixed point P injects into here. So we have both of these. So in some sense, this one is intrinsic and this one comes from choosing your global orientation. So how are you then supposed to pick your sign? So you look at the isotropic Grassmannian of maximal isotropic subspaces of this quadratic space, E fixed. This will have two connected components. So if both of these maximal isotropics live in the same connected component, you're supposed to take this sign as plus. And if they differ, then you're supposed to take minus. So that is the sign rule that you get. And you can actually write this in terms of formulae as follows. So this is joined with Jürgen Rennemo. So you can look at the composition of the differential, ds, and then project onto the maximal isotropic lambda and take the co-kernel. Then it turns out if you take the fixed part, that gives you the parity that you're after. So now we're going to make this concrete for the quivers we're looking at. So first, we need an actual torus action on our quivers. So let T be the following torus. So it's T1 up to T4 in C star. So these TIs, they just act on the loops in this big origami quiver. So maybe just to remind you, here we have this quiver with these loops. But we require one important property. The product of the TAs should be 1. And the reason we do this is because the quadratic form that you write down for either the origami quiver or the Hilbert scheme quiver has to be T invariant.
So it's a bit different from ADHM. ADHM would do the full C star square.
Right, that's right. Yes, yes. So here you really cannot get around this property. That's right. Yeah, somehow in the fourfold world, everything has to be Calabi-Yau. And then there's a second torus part, and this is just acting on the framing. It's the product over all A in 6 bar of C star RA. So this is just a diagonal action on these spaces WA. And we use coordinates WA alpha for this part of the torus. So all of this acts on this moduli space of representations. And in case of the Hilbert scheme, we also have this torus, but then we just leave out this second part. So in our setting, the first observation is from the explicit description that we have for the quivers, it's actually very easy to write down maximal isotropic subbundles. So again, I'll just do this for the Hilbert scheme. So in case of the Hilbert scheme, if we have a representation, x1 up to x4, I, which maximal isotropic subbundle can we take? So remember, for the full bundle E, we have 6 copies of the endomorphism algebra, labeled by A smaller than B, ranging between 1 and 4. And for lambda, we just take, well, one choice would be to take those copies where B is equal to 4. So if I go back to the formula, you can see that for this choice, this quadratic form that I wrote down here, this vanishes on the lambda that I took. So, and something similar you can do for the origami space. So let us pick this as our maximal isotropic subbundle. So what about the fixed loci under the torus? So in both cases, we'll have a zero-dimensional reduced fixed locus. So for the Hilbert scheme of points on C4, it's well known that if you act with the full four-dimensional torus, that the fixed locus consists of monomial ideals of finite co-length, which you can visualize as a pile of boxes in the corner of a large four-dimensional room, set bigger than or equal to 0, 4. This is how you would phrase it. And okay, so that's what they are, and I view my boxes as sitting on the lattice points, so we always have a box in the origin. But this is maybe a little easier for the origami space. So here it's just a huge collection of two-dimensional piles of boxes, two-dimensional partitions, in other words, Young diagrams. So for each A in 6 bar and each alpha from 1 up to the rank, RA, you're given a 2D partition lambda A alpha. So here I've drawn one, and we think of the boxes as sitting on the lattice points. So now what we do is, if we have a fixed point pi or lambda A, such a collection, I'll define some characters, some representations associated to it. So for pi, I just sum over all the boxes in my partition, finitely many, and I put T1 to the I, T2 to the J, T3 to the K, T4 to the L. And what do we do for lambda A? So for lambda A, we do something similar. So suppose this A is given by small a smaller than b. So we sum first from the rank alpha is 1 up to RA. And then again, we sum over all the boxes in our partition. And then it's TA to the I, TB to the J, WA alpha. So this time I also put this framing parameter WA alpha in. So these characters will come back soon. So the first theorem I want to mention is the following one on the Hilbert scheme, so joined with Jürgen. And in physics, this formula was discovered by Nekrasov and Piazzalunga. So the theorem says that if you put all the equivariant degrees of Hilbert schemes of points of C4 into a generating function, so you sum over all n, q to the n, and then Hilb n C4, this can be expressed purely combinatorially by the following formula. It's the sum over all four-dimensional piles of boxes, q to the power the size of the partition, and then some sign, which I'll explain, and some equivariant weight, which I'll also explain. And actually there's a closed formula in this case, which is, it's the exponential of minus S1 plus S2, S1 plus S3, S2 plus S3, over S1, S2, S3, S4 times Q. So I'll explain this notation too. Actually, this talk is not about the second equality. To show the second equality requires an entirely different set of techniques. So this talk is about this first equality. But let me explain what's in this formula. So the most interesting part is this sign here. So this sign mu of pi is the size of the partition, and then you're supposed to count how many boxes are there in pi of the form AAAB, with A smaller than B. So you see here that 4 is sort of a distinguished direction. It's asymmetric in 4. And that's because we picked this specific maximal isotropic subbundle, where 4 is also distinguished. And, but likewise, there's also, 4 will also be distinguished in this weight v pi here. So what is v pi? It's this representation z pi plus 1 minus t1, 1 minus t2, 1 minus t3, over t1, t2, t3, z pi dual. So dualizing here means each of the variables ta is replaced by ta inverse. And then this is just taking its Euler class. So this thing here on the right-hand side is something purely combinatorial that you can put into a computer. So if you would not put these signs, you get a mess. Only if you put these specific signs, you get this pretty formula here.
So the exponential, does like left-hand side is kind of clearly invariant under the 4, right?
Yeah, so this is also, okay, so let me first maybe explain what these SAs are. So what is SA? So if I take the equivariant first Chern class of the character TA, that's what I define to be SA. But we're on this smaller torus where T1, T2, T3, T4, their product is 1. So in terms of equivariant parameters, the sum of the SAs is 0. So yeah, if you work modulo that relation. Maybe I also forgot to mention that this, I didn't put it on the slides, but the virtual dimension of these Hilbert schemes is, of Hilb n is actually n. So it's unlike in the DT3 case, if you don't put any insertions, you just get, you don't get a number, you get something depending on the equivariant parameters. So this formula was conjectured by Nekrasov-Piazzalunga, as I mentioned, but their techniques look completely different. So they calculate some path integral, and then they get this answer.
Sorry, virtual dimensions 2n.
Yeah, complex virtual dimension is n, yeah, real virtual dimension 2n. Yeah. And I should also mention that this formula was also recently proved by Cao, Zhao, and Zhou using completely different methods, namely degeneration. However, they do not give you a formula for the signs, and in particular, part of our sign analysis is also required for their work. So now let's go to the origami quiver. So in the case of origami, the virtual dimension is given by this formula here. So it's minus the sum over A in 6 bar of RA bar. And you should not feel uncomfortable with negative virtual dimensions because we work equivariantly. So it's really a feature of this theory that it has a negative virtual dimension. In fact, we give a name to the first invariant. So if we put instanton number 0, we get some constant, which we call C, and physicists often call this the perturbative term. So yeah, now apologies for some more notation, which is due to Nekrasov. So if we take a fixed point lambda in our origami moduli space, and we take a capital A consisting of A smaller than B, then I already introduced this character z of lambda A. So that's this character over here. And we need some more notation. So n of A is the sum from alpha is 1 up to r of A of just these weights W A alpha. And then he also has this notation. Phi of A is the minimal element of this set. And we define P of A to be 1 minus TA, 1 minus TB, and P of 1, 2, 3, 4 as this expression, 1 minus T1, 1 minus T2, 1 minus T3, 1 minus T4. And then the key player is this character here. So this is T lambda of A, it's NA times Z lambda A dual, plus TA TB, NA dual Z lambda A, and then this quadratic term. But this thing is familiar, so as Jim was already mentioning, you sort of want to see these separate ADHM moduli spaces as well. And this one is precisely, if you take out a factor, this is precisely the tangent representation of the traditional ADHM moduli space at this collection of partitions lambda A. So then we have the following theorem with Noah and Woonam, and in physics it appears in Nekrasov's work. So what we do is we look at, again, the generating series of all these equivariant degrees of the virtual classes, so the sum over all n, q to the n, and then this integral. But we normalize by this perturbative term. So in some sense, this is a way of making it a virtual dimension 0 theory, because you take out a certain constant term that is in all of your virtual tangent representations. And then what the theorem says is that this is a purely explicit combinatorial formula. It's the sum over all tuples of partitions lambda, q to the total size of lambda, times some explicit equivariant weight. So what is this equivariant weight? V of lambda. So it's given by an explicit formula. It's the sum over all A of P of phi of A times this T lambda of A plus P A bar N A, and then the sum over all B not equal to A of Z lambda B dual, and there's some quadratic term. And this weight, we have to take the Euler class, and it also appears in Nekrasov's series of PPS CFT papers. But what it is for us is it's a halving of the virtual tangent bundle. So if you take this explicit formula and you add to it its dual, you get the virtual tangent representation. So this we call the origami partition function, set R of Q, and in some sense this is the analog of the traditional Nekrasov partition function. Now, the interesting thing of this theorem is what's not written on it. So what is not written is there's no sign. So what's special here is that all the signs are plus. So for origami, if you go through this orientation analysis, as you would do in the case of the Hilbert scheme, it turns out that all the signs are plus. And I think also in the physics literature this is new. So here there are no signs.
Is there a closed formula for this sum?
No, and in some sense there shouldn't, because for the traditional Nekrasov partition function there's also no closed formula, because it's supposed to be a rather rich object which goes into, it's a building block for things like Fafa-Witt and Donaldson-Thomas. So likewise,
The Hilbert scheme you had.
But and I'll also discuss a few special examples for low ranks where you do get closed formula. Yeah, so there are cases where you do, which I'll discuss in a moment. But in general, it's like the Nekrasov partition function. It's not supposed to have a closed formula. So the key feature here is that what's interesting is that even though the origami quiver looks quite different from the Hilbert scheme quiver, the sign analysis for the origami quiver is identical to the sign analysis for the Hilbert scheme quiver. So if you take a fixed point P, consisting of x1 up to x4 and IAJA, so what are you supposed to do? So you're supposed to look at the co-kernel of the differential of S, going from TA at a fixed point to EP, and then you're supposed to project onto lambda. Then you want to take a fixed part in the co-kernel. Now, even though E and the ambient space, it all looks quite different in the origami case, the miracle somehow is that after taking the fixed part, you end up with precisely the same map that you encounter in the setting of the Hilbert scheme. So the one that I analyzed with Jürgen. So it becomes, to be concrete, at this fixed point, it just becomes the map from 3 copies of the endomorphism algebra to sum over all A in 6 bar with A smaller than B smaller than 4 of NV. And you're taking matrices YA and you're mapping them to commutator XAYB plus YAXB. And again, actually calculating the parity of this co-kernel is not easy, but we already did it in this work. So that can then be fed into the origami story. And actually a similar phenomenon happens for yet another setup that was studied by Fasola and Monavari in mathematics, and Pomoni, Yan, and Zheng in physics. So these are the so-called tetrahedron invariants. So what are they? So in this setup you look at affine 4 space and you look at the union of the 4 coordinate 3 planes, C3. So let's call this delta. And what they do mathematically is they look at quad schemes of a certain sheaf on this singular 3-fold delta. And quad n means we're looking at 0-dimensional quotients of this sheaf. So what is the sheaf? So for each copy of C3, from A is 1 up to 4, you just take RA copies of the structure sheaf and push it forward. So this is the quad scheme you look at. And then what Nadir and Sergei showed is that this has an O-Thomas virtual cycle, which produces what they studied in physics. And in fact, in this case, there is a nice formula. So if you put all the degrees of these virtual classes into a generating series, you get McMahon of a sign -1 to the R times Q. So R here is the total rank, if you sum up all of these ranks. And then there's a power that looks the same as we saw in the Hilbert scheme of points case on C4, this power here. And then there's this new factor, the sum over all A of RA times SA. So M here is the McMahon function, MQ. It's the product over all n positive of 1 over 1 minus Q to the n. This is the series that enumerates piles of boxes in the corner of a 3-dimensional room. But what's interesting here is that, like for origami, the sign analysis reduces to the sign analysis done with Jürgen. So let us go back to origami and address Jim's question, are there some formulae? So the first case you could look at is let's only switch on one framing. So R12 is R and all the other RAs are equal to 0. So then the moduli space is just the traditional ADHM moduli space with equivariant parameters T1, T2 and framing parameters W1 to alpha. So in this case, this origami partition function is just equal to an integration over the traditional ADHM moduli space, MRN, but there's an insertion. So now you're not integrating one, but you're integrating the Euler class of the tangent bundle twisted by T3. So 3 is one of the other directions. So this, if you like, this is what you could call the Fafa-Witten invariance of the affine plane C2. And in fact, yeah, these can be used to also calculate Fafa-Witten invariance on compact surfaces that we heard about in Richard's talk. So the old ADHM story is in here. So already at this stage you need the sign analysis because you better have that all the signs of the partitions are the same in order to get this reduction. So somehow the fact that the sign is everywhere plus feeds into everything in all the formulae that follow. A second example is let's take all ranks RA4 equal to 0, so no framings in direction 4. So A varies from 1, 2, and 3. And let's go to a slightly smaller torus. So previously we had that the product of T1, T2, T3, T4 is equal to 1. So now we also put T4 equal to 1. So we have this smaller torus T0. So in this case, the moduli space has a different description. So in this case, it's easy to write down a smooth ambient space A0 with a superpotential on it, a regular function, such that MRN arises as the critical locus of this regular function. And it's a T0 invariant regular function. That's why we restrict to this torus. So this setup was studied by Rabchak, Soibelman, Yang, and Zhao, and they study cohomological Hall algebras of this moduli space. So a special case of origami. So in this case we have two virtual classes. We have the O. Thomas virtual class, but since we have this critical locus description, we also have a two-term symmetric obstruction theory, and therefore we have a Behrens-van Tecke virtual cycle too. And it's easy to show from the main theorem that actually they give the same answer. And for those in the audience who like the Behrens function, we also calculated the value of the Behrens function at all of the fixed points, and it turns out to be always +1 in this case. There's no Behrens sign.
So can I just ask, so that proof is also why the torus fixed points?
Yes. So the proof is really by localizing both sides and then identifying them. Yeah. And again, it depends on also knowing that all the signs are the same, because otherwise it would only match up to signs. So in fact, you can put them in a generating series, and it's just eta bar q to the minus r. So this here is the normalized Dedekind eta function, product over all n positive, 1 minus q to the n, and r is the total rank that we have here. So this object here is counting two-dimensional piles of boxes. Now let's also do one truly four-dimensional example. So let us take, as in the beginning, framings R1, 2, R3, 4 equal to 1, and all the other RAs equal to 0. So in this case, we also have a closed formula for the Nekrasov, for this origami partition function. It's eta bar of q to the power minus s2 plus s3 s1 plus s3 over s1 s2, and then a second factor, the same to the power minus s3 plus s1 s4 plus s1 over s3 s4. And what is surprising about this formula is that it does not depend on the framing parameters. So the framing parameters somehow drop out, and that allows us to actually find the closed formula. So at the background of the proof of this theorem is one key ingredient. So if you're on a quiver moduli space, in fact in this case the stability can also be realized as a king stability, there's always a map to the semi-simple representations, which is a projective map. And in this case, the quiver is easy enough that you can actually write down what are all the semi-simple representations, and you turn out to get sim n of C4. So somehow the push forward to here plays an important role in the proof of this formula. So it's used to show that there's no dependence on the framing parameters, and then we can do an explicit calculation. Okay, so are there any questions about the quiver side? So in the final part of the talk, I would like to at least make a few steps towards a sheaf description of this moduli space. So yeah, maybe also, as I said, we have this property 1 we already had, and this should be the analog of the Nekrasov partition function in this fourfold setting. And if you like, maybe this example here, in a way, you could view this origami partition function as something that looks like Vafa-Witten theory of a singular four manifold, or at least the local version of that. Okay, so now we go to sheaf description. So let us go first to the following general setup. So let X be a smooth projective fourfold, and let D be an effective divisor such that twice D is anti-canonical. Let us fix a Chern character with the first two entries equal to 0 in the cohomology of X, and let us fix a pure one-dimensional sheaf on this threefold, on this effective divisor. This effective divisor is allowed to be singular, and in fact we'll take it singular in a moment. So we'll look at the following moduli space of framed sheaves. So we look at pairs E, phi. So E here is a pure two-dimensional sheaf on X, and phi is a framing. So it's an isomorphism between the restriction of E to the threefold. So we're intersecting something two-dimensional and three-dimensional. So we want to compare it to something one-dimensional, namely the fixed sheaf, one-dimensional sheaf F on D. And then we take the Chern character of E to be V. So it turns out that isomorphism classes of this form a quasi-projective scheme with a universal family. So technically how you achieve this is, so Hilbert and Lane have this notion of moduli of pairs, where they map from, they fix a sheaf and they look at maps from a sheaf E to the fixed sheaf. There's a notion of stability there. It's not true that you can pick your stability so that you immediately get this, but this is an open subset in their moduli space of stables for the right choice of stability. In fact, something similar can be done for the ordinary framed sheaves moduli spaces on P2. Okay, so this is the moduli space, although it is a non-compact moduli space. And then it has a three-term symmetric obstruction theory, omega M framed Ver mapping to the truncated cotangent complex. So what is this virtual tangent bundle pointwise? So over a pair E, phi, it's the derived Hom of E, E twisted by minus D, shifted by 1. So the point now is, because this D is, twice D is anti-canonical, this complex here is self-dual. So this is some sort of square root log setup, if you like. So now, whenever you fix an orientation, O. Thomas's paper will give you a virtual class in the Chow groups. So in here goes an important technical point. So in order to apply Borisov-Joyce or O. Thomas, you need your moduli space to be the truncation of a -2 shifted symplectic scheme. But it turns out, lucky for us, that Theodore Spade, in his thesis, he actually showed that this is the case for M framed. So it's the classical truncation of a -2 shifted symplectic derived scheme.
Where's the F? The F doesn't appear in the...
Oh, where is an F? Is there an F?
From the previous page. Or,
oh, yeah, okay, so...
fix this.
Right, so yeah, because this is an isomorphism, yeah, the F doesn't appear.
Oh,
yeah.
E restricted, that was the test. Sorry, okay,
Yeah.
that's the honesty, sorry.
Can you tell us why this problem gives us a moduli space which looks like Calabi 04?
Well, yeah, all I can say is that, So yeah, if you would have just D in the anti-canonical, then X take away D is like log Calabi-Yau 4, but then in addition you sort of want to have. And that's apparently, so apparently what he shows very generally is, he has some very general setup, not specific before, but he looks at this setup in any dimension. So you have an n-fold, a divisor, twice D is anti-canonical, and then he shows there's this shifted symplectic structure. But yeah, I'm not able to answer it in a good way. But I do want to point out one other thing. We do not construct orientations on this moduli space. So hopefully Dominic Joyce and Marcus Uppmeyer and others can construct orientations for us on this moduli space. So the upshot now is to use this general setup to recover the origami quiver from the beginning of the talk. So I'm now going to pick a specific X and D and F, which will produce the origami moduli space, or at least the invariance. So what we do is we take X to be P1 cross P1 cross P1 cross P1 with coordinates xi, yi, zi, and fi. Actually, in the ordinary ADHM setup, you could also have worked on P1 cross P1 instead of P2. From our point of view, that's the right thing to do. You should not work on P2. So that's why then it looks more similar to what we're doing here. And as your divisor, you take the following singular threefold. You take the product of x0, y0, z0, w0 equal to 0. And now we have 6 surfaces, all isomorphic to P1 cross P1, which are the following 6. So S12 is Z1, W1 equal to 0, etc. So each of these 6 surfaces will intersect this threefold at infinity in a line. And what is this line? Or in a curve? This curve, LA, the intersection of SA and D, it is a union of 2 P1s meeting in a point. Actually, it's quite instructive to first do the case where you have 3 copies of P1 and then draw all of these surfaces and divisors. And now comes the other key point, which framing sheaf do we pick? So we need to pick a one-dimensional pure sheaf on this threefold. So we take the direct sum over all A in 6 bar of OLA to the power RA.
Sorry, when you fix this pure one-dimensional sheaf, do you need it to be a smooth point in its moduli space?
I don't think so. So I think that can be an arbitrary point. And then as our Chern character, we take the sum over all A in 6 bar of RA Chern of OSA. And at least you immediately then find that you get the correct virtual dimension. So the virtual dimension is again negative. It's minus sum over all A in 6 bar of RA bar. I mean, this formula, it looks a little bit like if you're doing surfaces on compact Calabi-Yau 4-folds, you also get often negative virtual dimensions. Then it turns out you can reduce to make it positive again. But somehow in this equivariant setup, yeah, we don't have to reduce, we can just work equivariantly. And it's fine to have negative virtual dimension.
You don't
yes?
have a virtual cycle though? Because it's negative.
Well, equivariantly, there are negative degrees in homology. So.
Yeah, but okay, you're not localizing a virtual cycle. Like you're not even.
But yeah, but yeah, at this stage, yeah, for sure we also need. So that's the second part. We need this torus, and okay. So what is the torus in this case? So it's a C star cubed. The C star cubed that acts on X take away the divisor, and we have this framing torus that acts on FR. And then our moduli space MXV. Let's just denote it by MR bar n framed. But yeah, in a way you could say we define our invariance by localization, but the point somehow is to get interesting answers, you need to be able to induce your orientations from a global choice of orientation. So in some sense you could say you can always define invariance by localization, but experience teaches you that to get interesting answers, your orientations need to be induced by something global. So how do we now connect to the origami side? So, so on both sides, the sheaf side and the origami side, we can act on our moduli space by just the framing part of the torus. And then you get what Jim said. So then you actually get copies many copies of the traditional ADHM moduli space. So both of these moduli spaces have the same fixed locus with respect to the framing torus. And it turns out both of these framing fixed loci, they sit in the same connected component. So they both sit in an entire connected component, both on the sheaf side and the origami side. In fact, it may well be that these two moduli spaces are connected, but we cannot prove it at the moment. So for both, we show that this fixed locus, which itself is disconnected, sits in one connected component on both sides. And then what you may hope is that that connected component is actually the same, so that there's an equivariant, T-equivariant isomorphism between these connected components, which on the one hand respects these inclusions of fixed loci, and which on the other hand intertwines the virtual structures. So this is what we hope, and if it's true, this could be viewed as an analog of Bart's result. But what we show is, at least on the level of invariance, something like this is true. So because we already have this, it's easy to see that the fixed loci for the full torus are the same. And then the interesting thing is that the virtual tangent representation on the framed side, so that's this R-hom E, E twisted by minus D, that actually matches the virtual tangent bundle you get on the framed side, the origami side. So there's a match of virtual structures here. But again, we have some advantages on the origami side because here we have full control over the orientations, and at present we do not know how to construct orientations on the sheaf side. Yeah, I think this is a good place to stop.
Thank you very much. Are there any questions?
Your framed sheaf moduli spaces, you probably said this, but I missed it. It's not compact, is that correct?
Yes, it's not compact.
That's not a problem because of the C-star.
Right, exactly. Yeah. So this theory is only works if you are on fourfolds where you have a big enough torus acting. Yeah.
Okay, nice.
So you said that you have negative virtual dimension. Usually reducing, you can, let's say, remove this problem. Have you tried to see at least for, I don't know, for low n if you can actually do this? Like if there are some pieces that you can remove to make it positive again, the virtual dimension?
So yeah, it's definitely analogous to the setting that for two-dimensional sheaves on compact Calabi-Yau fourfolds. If you don't reduce, you get negative dimension, and indeed you can reduce using Hodge theory methods. But in this equivariant setup, I do not see how you can reduce. And in some sense, you normalize by this the zeroth contribution. So that's what I wrote all the way in the beginning. So you always normalize by this perturbative term, which is actually kind of, if you work with Vafa-Witten invariant, you also always have to do something like this. So this is, in a way, this normalization is at the level of formulae, it is making its virtual dimension 0. So maybe this is some sort of crude way of reducing. But it's not a geometric way of reducing. But it turns out this you also do when you do Vafa-Witten theory.
I think we discussed this before, but what is exactly, I mean, you have a very beautiful, very clean conjecture now. What's the problem with hitting it with some kind of Bayesian resolution? Or?
Yeah, so this, I mean, there's some very low instanton numbers for specific values of RA where we can produce enough sheaves to really show that this is the case. But yeah, I mean, this is the direction you want to go into. So you really want to have an analog of that construction in this setting. Yeah.
Yes.
Maybe just a very general question. For the usual Nekrasov partition function, does this equal blow-up equations? So they would behave sort of blowing up C2 at a point.
Right.
And I'm wondering if there is any analog for this C4 situation.
Yeah, that's a very good question. Yeah, so this is yet another direction.
Quartic relation.
Right.
Yeah,
yeah, this is certainly not something we thought about. But there are all kinds of directions one can now go into. Like the first one, another one I should mention is that at least here I presented everything cohomologically, but the entire story can be done as we learn on Monday. We should work K-theoretically these days, so you can also do everything K-theoretically with virtual structure sheaves. And then in Nekrasov's papers, he goes into another direction where there are additional finite group actions on the C2s. And so there are a lot of similar things you could try to attempt in this more general setting.
I have another question along these lines. In the ADHM case, the relations could be interpreted as imposing the zero set of a moment map for the torus action. So what you get is a symplectic or hyperkähler quotient. Now I understand that these are shifted symplectic spaces, but still, is there any interpretation of that kind? And if so, is there some virtual way of resolving singularities by moving to a regular value?
Yeah, so I don't know, but certainly Nekrasov comes more from that side. So when he writes this down, he doesn't immediately write down these holomorphic equations. He actually writes down moment map equations, and sort of the real part plays a role in his equations. I mean, we just straight away zoomed in on the complex part. But yeah, these are all very interesting questions.
All right, are there any further questions? Yes, Thomas.
So, when you had this thing with the restriction to the sheaf at the boundary, if you're going to get something -2 shifted symplectic, it must have a virtual dimension. How does the virtual dimension depend upon the choice of the sheaf at infinity?
Yeah, so it's in so actually, yeah, in general, yeah, we have no general formula because we only applied it in this case of this product of P1 plus P1 and this specific sheaf, and then we calculated and it gave the right number on the origami side. But yeah, we haven't really tried to look at other sheaves, so I don't quite know how the chunk characters of that sheaf come in general. Yeah, I'd have to think about that.
I mean, you get it from the long exact sequence, right? Relating the x of E and the x of E twisted by -d, and then the x
Right.
of the sheaf at infinity.
Mm-hmm. Yeah. Yeah, we just did it only for this example. But yeah, that should be easy. Maybe only I think maybe only the second churn character. Well, okay, yeah, I'd have to think about it.
Are there any more questions? All right, so we resume at 3:30 with Daniel Alpenmeister, and meanwhile, thanks again to Martijn.